So I would like now to tell you a little bit about what is kernel. So kernel stands for Quantum Exploration and Research of Noisy and large scale, this is the L, large scale computing. So, but it's really nice. So what it is about, it's essentially a proposal to establishing a center which will be funded by the Council for Higher Education through the Planning and Budgeting Committee, PVC. So it really came, so there is a call for establishing those centers, both in the regime of algorithms and for the hardware. This is, of course, a proposal to establish a center in the hardware side. And first of all, I would like to acknowledge all the PIs that wrote the proposal, and which belong to 7 universities. I would like also to tell you a little bit how this came about. So the group includes people who are interested in near-term quantum computers. And I would like to really open my presentation with a statement, which is that quantum computing is real. So it started in the 80s as an idea, as a proposal by Feynman and Deutsch. And really the revolution came about in the last decade, in 2016 and 2019, by IBM, who offered the quantum computing on the cloud. At the beginning, this was a 5 qubits quantum computer. Very close, around the same time, with a beautiful experiment by Google that stand the time, right? We are now 6 years after this experiment, and no classical calculation was able to reproduce those results in as short time as the Google experiment. And today, we have tens of QPU manufacturers. So here you can see a table that is taken from Quantum Insider. I added the line about these startups that were created in Israel, and then we have here even representatives from those startups. I think it's interesting to see that, first of all, it's a worldwide effort in the Americas, in Europe, and in Asia. And also, I think the columns are also interesting because they are telling us that this is a technology that is developing. There are many different platforms. It's a little bit small. I hope you can see superconducting, silicon, NV centers, trapped ions, neutral atoms, photonics, and more. So it's not clear what is the technology that will lead the true revolution to quantum advantage. But there are many proposals, many factors, and this is something that exists. I mean, whether you think it is useful or not, I think it is important to acknowledge that those computers exist, and it is important to connect them to the research, to the actual research. And this is what kernel really wants to do, so to create a link between real existing quantum computers and research in the academia in Israel. So we have 3 strategic goals, which are, first of all, the audience, the student in the audience, to grow the next generation of masters and PhD students, and also postdocs, and eventually, new PIs that will lead quantum computing. And we already know that all those startups that were created in Israel, eventually they are established upon the students that we grew up. So it's really working, and it is important to continue that effort in the future. We will have meetings and interprofessional conferences. So this is actually an example, and I think it's really promising. I think I heard a lot of good, positive feedback from the people in the audience, and we'll have more of those. More regular, so that we know each other and we really create a community, and not just the isolated PI in the different universities and faculties. And I think an ingredient that is very important for that to work is that we will be able also to use those quantum computers. So we heard here the talk by Sabine, who told us how important it is for her university to have access to those quantum computers and to play with them and see what can be done, what cannot be done, what is possible, and what will be possible in the close future. And we'll allocate a budget for that purpose. So we have collaborations with several companies that are just manufacturers of quantum computers that they can provide access for a payment. So in addition to that, we have scientific goals. I mean, the idea is not just to run on neutral, but to do some interesting research and to advance our understanding of many-body and open quantum systems. And we define, and the way it really went is that we sat down all the 20 plus researchers, and we just wrote a list of all the topics that we are interested about. And then we try to, to sort of divide it in different groups, because we understand that, you cannot, possibly even write a proposal 23 people together. So we divided ourselves into groups, and this is a little bit represented in the program today. So the different students come from different work packages. And the work packages are noisy algorithms, open quantum systems, and quantum simulations. And what I would like to do now is actually to invite sort of one researcher representative of that work package who can tell us very briefly about what is the work package about. Of course, it's not an inclusive list of all the things that belong to this work package, but the idea is to find collaborations and strengthen those interests, because clearly, one cannot force a PI in the university to work on a specific project unless he's really passionate about it. And that's what came out. And this is also the reason why we are here, because we heard that people, at least I myself, was so interested about the things that everyone was talking about, said I need to learn more about it. So I would like to invite Eliahu on the stage, who can present briefly, just in a couple of minutes, what the work package is, or the way you see it.
Thanks, Emanuele. So, hi. Yeah. Great to see all of you. It's exciting to have this inaugural meeting. First of all, I'd like to thank Emanuele. He said, let me tell you how things came about, but this wasn't really the case. Emanuele personally talked with most of the PIs here and told them, look, this is very important to me, this is very important to Israel, and I want all of us to do it. And eventually we did. Emanuele organized the proposal and this event, and we thank him very much for doing that. Let me tell you just briefly about the first work package number 1, concerned with noisy algorithms. First, I think I have to explain that there will be several hubs in Israel, part of which will be devoted to hardware, and 1 or 2 will be devoted to theory. And as a theorist, we decided to focus on what can be done right now or within the next few years. Some very good algorithms are known to work very well on fault-tolerant quantum computers, but currently we don't have them. We have low-depth circuits with hundreds or maybe in the near future thousands of qubits. And we need to find suitable algorithms which can bring us interesting results despite the major noise that we have and despite all limitations which came about once we limit the depth of the circuit. And this is basically where variational quantum algorithms and QAOA were born. And this is the essence of the first task here, concerned with optimization problems. People realize that quantum computers might be able to solve well or approximate the solution of several optimization problems, yet many challenges exist today, most of which related again to noise and the depth of the circuit. Another major problem is known as Bar-Ilan plateaus. So the variance in the cost function is exponentially decreasing with the number of qubits and the depth of the circuit. And we need to find ways of choosing better ansatz and actually to have a different paradigm, a paradigm which is based on hybrid quantum classical computation, some merger of QPUs and GPUs. Part of this effort was presented in the previous talks, and we plan to continue this effort forward by having what was previously mentioned as quantum-informed neural networks. And this brings us to the second task of quantum machine learning. And here we have another problem, but this problem is not technical, it's a conceptual problem. Till now, we have quantum SVD and quantum SVM, support vector machine. We have quantum PCA and quantum neural network. All these are attempts to quantize classical machine learning primitives. But probably this is not the best way to proceed forward. We need to find quantum native algorithms, one which harness from the very beginning the principles of quantum mechanics. And once we do that, we might be able to overcome the previously mentioned problems, and then we can also try to solve some interesting problems related again to optimization, but possibly also to partial differential equations mentioned earlier, maybe also to quantum chemistry, and so on. In the next work package, we are really relying on low-depth circuits, and we use these circuits for computation in the general sense. In this work package, we broaden what we call quantum computation, and we also analyze entangled networks, we analyze communication, cryptography, and in all these tasks, the benefit is we don't really have to use very deep circuits. The number of gates is relatively small, and nevertheless, we can experience with the effects of noise on entanglement. We can make experiments and see how these small-scale quantum networks behave. And this is not only a sub-effort in the sense that entanglement certification via quantum games is very helpful, but it's a goal in itself, because people are now interested more and more in quantum and quantum-inspired models for funding and for voting. And all these tasks can be realized even now on quantum computers, even when the errors are not so small. So this task is very feasible with nowadays tools. And the last one is the second side of the machine learning quantum coin. Earlier I discussed how quantum mechanics may assist machine learning. In this task, we try to harness classical machine learning in order to improve quantum computation. So we use known models based on deep neural network, deep reinforcement learning, diffusion models, and so on, for improving the pulse engineering and improving error correction and error mitigation. With all of these together, we plan to solve new problems. We first want to find new problems which can be solved using noisy quantum computers, and then we really want to do it efficiently, not only in terms of gates, but also in terms of qubits, in terms of total time, sampling, number of shots, and so on. So there are many constraints here, but luckily we are a large, diversified group with a multidisciplinary effort consisting of computer science, physics, chemistry, data science, and more in order to solve these great challenges. And hopefully together we can do it, not only within this work package, but also via collaborations with the other two work packages, which will be presented now. So I guess...
And again, I want to thank Emanuele for everything he did, almost single-handedly. So this work group is essentially all about noise. That's the key theme here. The first two work packages are about trying to reduce the noise, and the other two are about simulating it and exploring it using essentially classical computers. So the first work package is about error mitigation, and maybe let me clarify the terminology. So when trying to reduce noise, there is correction. Everybody knows about quantum error correction code. There is suppression. Suppression refers to all sorts of pulse engineering techniques like dynamical decoupling, drag pulses, things like that. And there is mitigation, where mitigation is a post-processing technique where you learn something about the noise, and then in post-processing, you pay in runtime overhead in order to mitigate the noise and try to distill what is the noiseless expectation value. Okay, so there are three different things, and it's actually interesting to see how to put them together, because they all have their own advantages. For example, error mitigation works on a broad scope of errors, but the overhead in time is exponential. Okay, so it's not a way to scale up. It's a way to take a device which is not that good and make it excellent, but not more than that. On the other hand, error correction, we are not truly expecting that it will work perfectly. There are correlated errors, there are leakage errors, there are all sorts of things that, and even if it works very well, we will want more depth or more qubits, and we will reach this regime again where the noise becomes a problem. And by combining error mitigation and error correction, maybe it's a way to give some performance boost beyond what error correction can give. So this is what we want to explore in the first work package. In the second one, it's written mitigation, but it's actually suppression. It's all sorts of technique that generalize dynamical decoupling, and sometimes based on learning, actually, the noise in the given circuit, and then use it in order to design pulses that avoid, if you wish, the noise as much as possible. And the last two work packages are about simulating, and in some sense they will support and help develop the first two work packages. They're about using advanced simulation tools, for example, by Guy Cohen here, and also Oded Hod, whether to simulate with realistic noise models, including non-Markovian effects for several dozens of qubits, and even see how they manifest when running an actual algorithm, or to go to a more fundamental level, what Oded Hod is doing, and really see, do all sorts of time-dependent density functional theory to really better understand the onsets of the noise mechanisms in atomic platforms, let's say Rydberg atoms or trapped ions. So I think that's about it. Let me just say that. Yeah, I think I'm done. Okay, so. Okay,
thanks. So hi, I'm Jonathan Ruhman from Bar-Ilan University, and I'll present the last work package, quantum simulations and many-body physics. And the way we chose to look at this work package is actually that the NISQ devices, we can view them from two different viewpoints. The first is as quantum simulators. They're very clean quantum systems, and we can run simulations on them. And here there are a bunch of problems. I don't want to elaborate too much because we're short on time, but maybe I'll emphasize a few. So mapping computational problems to Hamiltonian dynamics, and this can be related to work package 1.1 for collaborations. Simulating exotic quantum matter such as topological order, gauge fields, maybe quantum gravity, quantum critical points, and so on and so forth. Realizing entangled or resource states. So we heard today about resource states, cluster states, so to try and realize them on computers to test them. and then foundations of quantum mechanics. And then the second viewpoint would be to study NISQ devices as many-body systems themselves. So one of the things that we're interested in is studying quantum information dynamics in monitored and open quantum systems. This can be related to simulation in work package 2.4 because the fact that the system is open means that the amount of entanglement in quantum trajectories is reduced, and possibly we can leverage that for quantum simulation. Another point is thinking about engineering the system or the environment to create better results. And then finally, also heard today about these search algorithms from today's talk. And that's, I don't want to take too much time. So, Emanuele.
Okay, thanks, Jonathan. So I hope you had sort of a clear overview of what this project is about. Let me summarize very briefly to say that it's, all these work packages, they are really very much interconnected. I had a huge problem when placing the pictures before because everyone wanted to be in all the work packages. I said, no, it's too busy. So there was a problem with that. I think, yes, it's interdisciplinary, as one mentioned already before, and it's also practical. So we see these quantum computers as a true motivation, as an inspiration to do better research and studying new problems. The word scalable here is very important. So we really want to follow the transition between the near-term quantum computers that we have today and the one we will have in 5 or 10 years from now. And this is really a problem of scaling. So one needs to, we believe that the way to reach there is to slowly grow as the hardware grows and develop the algorithms that can go from where we are right now to where we should be in the future. And I think Israel is important. I mean, after all, this is public money. I think it is important to acknowledge that from the Council for Higher Education. And we would like to position Israel as a key player in the global quantum landscape. So, of course, international collaborations is something that is very important to us, and we will continue to do that. At the same time, we also need to strengthen the local kernel of researchers. There is one last slide I wanted to show you related to this interconnection. So again, we tried to make order out of these work packages and people, and it was really sort of impossible because everyone wanted to work on everything, and I think we are a really nice team. We have a website, kernel.org, so you can visit there. We will publish more information about fellowships that we will offer, so it's interesting for the students as well. And events like this one and futures, and yeah, so that's it. So thank you for listening, and again, thank for everyone for the huge effort that was made in this proposal, and hopefully it will be successful.